Hi everyone, this is lesson 5.3, using angle bisectors of triangles, and we're also going to talk about the incenter of a triangle. The incenter is the point of concurrency of the angle bisectors, just like the circumcenter is the point of concurrency of the perpendicular bisectors. So first of all, an angle bisector is a ray that divides an angle into two congruent angles. So here we can see that angle XYW and angle LYW are marked congruent. Therefore, YW is an angle bisector. So here angle XYW is congruent to angle LYW. Okay, so no news there. I think that you probably already knew what an angle bisector was. Now we just have a formal definition. And then here, one thing that's important is the distance from a point to a line is the perpendicular segment from that point to the line. Okay, so and you've already known that too, but for the angle bisector, we're going to talk about the angle bisector theorem, which uses that concept. Okay. So the angle bisector theorem says if a point is on the angle bisector of an angle, so here we would be talking about point D is on this angle bisector, then it is equidistant from the two sides of the angle. So it would be equidistant from side AB and side AC at the shortest distance, which in this case would be B and C, because that's the perpendicular distance. That's the length that's perpendicular. So this is kind of like the perpendicular bisector theorem, except the perpendicular bisector theorem said that any point that is on the perpendicular bisector is equidistant from the vertices or the endpoints of the segment that's being bisected. So with perpendicular bisectors, it's equidistant from the endpoints, or if you're talking about a triangle, it would be the vertices. But for angle bisectors, it's equidistant from the sides. And then those sides would have to be at a right angle. Okay, so I don't want you to get confused when you see segments that are equidistant from the sides and marked with right angle symbol and a perpendicular bisector. So a perpendicular bisector will be a right angle, but it'll also be at the midpoint. Remember, bisector means that it cuts at the midpoint. Okay, whereas one of these, they may not be on the midpoint of the triangle. Okay, maybe if it's equilateral or isosceles. Right, so I don't want you to get confused with those. Just know that there's a difference. All right, and then also when you've got these segments here, these will be congruent. All right, so for your perpendicular bisectors, they're not always going to be congruent. So we're just going to see if there's enough information to figure out if the value of x. So here, we know that this would be an angle bisector, this ray, and we know that this is a perpendicular line, so it's the shortest distance. Therefore, from the perpendicular bisector theorem, we can say that it's equidistant, so x would be 15. All right, let's do another, was there another example? I guess not. Okay. So the converse then states that if a point is in the interior of an angle, so point D is anywhere on the interior, just pretend that AD isn't marked there, and it is equidistant, and important here, equidistant and perpendicular to or from the sides of the angle, then it lies on the angle bisector. Okay, so point D has to be both equidistant and perpendicular to points B and C in order for you to conclude that it would be on the angle bisector. All right, oh, here's our second example. Is there enough information to determine if QS bisects angle PQR? Well, angle S is equidistant from P and R, but it's not marked perpendicular, so we wouldn't be able to say whether it does or not. So no, PS would have to be perpendicular to, excuse my poor handwriting this morning, perpendicular to QP and QR. Okay, so a few other examples. Find X if possible. Well, here by the converse theorem, we know that this point would lie on the angle bisector because it's marked congruent from the sides and it's at a right angle. So we could say that 6x equals 2x plus 16. So 4x equals 16, x is 4. How about here? Here you wouldn't be able to say so because you don't have angles marked congruent. You have a right angle here, but you don't know that these are congruent. So not possible. Not enough information. For number 5, if P lies on the bisector of this whole angle and GP is equal to, where's GP? 3x plus 6, then what is HP? So the idea here is that these two would be the same. And I think, okay, they're giving us side lengths here. So this would be 3x plus 6. So one thing we could do, if we know that this is an angle bisector, we could say 13x equals 11x plus 8. So that'd be 2x equals 8, and x is 4. So if x is 4, and they're asking for HP, then we could plug just 4 into x here. So 3 times 4 plus 6 would be 12 plus 6 is 18. So HP, since GP is 18, then HP would be 18. All right, and then this is just a similar problem. We're going to go ahead and skip this one just to save some time for you. And now we're heading into the point of concurrency of the angle bisectors. Okay, so just to review, concurrent means 3 or more lines that intersect at a single point. So a point of concurrency is just that point that we're talking about. A circumcenter is the point of concurrency of the perpendicular bisectors. I'm going to say POC, point of concurrency of the perpendicular bisectors. The special property of this one, which you will want to put in your little spreadsheet, is that the circumcenter is equidistant from the vertices of the triangle, and that the circumcenter is the center of the circumscribed circle. And then the incenter is the point of concurrency of the angle bisectors. And then we found out from the angle bisector theorem that it's equidistant, and I'm going to say and perpendicular to the sides of the triangle. And also there's going to be an inscribed circle. So it's the center of the inscribed circle. All right, so here your incenter theorem says that the incenter of a triangle is equidistant from the sides of the triangle. So this is kind of like the angle bisector theorem. So it says if AP are angle bisectors, so these guys are angle bisectors. And then this is what I was talking about in the first slide. So you would know that these three are congruent. Now these are not perpendicular bisectors. They're perpendicular and they're all congruent to each other, but they're not bisectors. So if you see something like this, it's because it's the incenter theorem. So there's your incenter. Okay, and then just some examples here, just seeing what's congruent. So here you know that this is an incenter because, well, I think it tells you that it's an incenter. Therefore, these sides here that are perpendicular, they're equidistant, and you would just set them equal to each other and solve for x. All right, there's nothing much more to that question. Okay, some more complicated examples. Once again, these are not hard to figure out. NF, it would just be 2, because here you've got angle bisectors and you're following the incenter theorem. So these 3 segments would be congruent to each other. Okay, so these questions here are not that hard. All right, so at this point, I'm going to take you to one of the GeoGebra applets that I thought was pretty cool. So here you've got a triangle. Now, and the angle bisectors are marked, and so are the incenter theorem markings. Okay, so you've got these 3 that would be following from the incenter. Now, if I take point C and if I move it around, well, I hope this is going to work. I don't know why I'm flashing here. I might need, oh, I know, it's because okay, here we go. All right, so if I take this, what if I try to make an obtuse triangle? See how the incenter still lies inside of the triangle? And even if I tried to make a right triangle, it's still gonna lie inside of the triangle. So the incenter is actually always gonna be inside of the triangle, whereas the circumcenter was either inside on the hypotenuse or outside of the triangle, depending on if it was acute, right, or obtuse. So one of the things it wants you to do is, I'm going to make this smaller, and then it wants you to create an inscribed circle, construct an inscribed circle with center at the incenter and going through the vertices. So if I did that, hold on a second. Oh, I see. I'm sorry, you guys. Let me try this again. Oh gosh. Undo. Okay, I'm sorry. The sides should not cross through the vertices of the triangle. They should cross through the sides of the triangle. There we go. Okay, so an inscribed circle has the center at the incenter, and the outside goes through the points F, E, and D, the sides of the triangle. All right, so that's another thing you can add to your notes. Maybe copy down this diagram and include an incenter, or on your spreadsheet, you can draw in an inscribed circle. Okay, maybe using a compass if you have one, or just, be very careful with going through the sides of the triangle. Okay, so now that's all of this lesson, and I hope you guys have a great day.